Okay, the law of exponential change. So, if y changes at a rate proportional to the amount present, that is if dy dt is equal to kt, okay, so let's do an example. All right, just think about this. If you have water leaking, all right, out of a container, when you double the amount of water, this could double the rate at which it leaks, maybe because the pressure is pushing down more, right? If you triple the amount of water, it triples the rate of leaking. That's what it means. That's what it means when it says proportional to the rate of the amount present, all right? So this is a direct proportionality, right? You've seen like, oh, y is equal to kx, a direct proportionality. Well, here the rate is proportional, right? So dy dt is equal to k times y, right? So this k is a constant. So you've seen this in chemistry, right? So in chem, you have something like V equals KT, right? The volume and the temperature are connected, right? They're direct proportionality. If you increase the volume, you are decreasing the temperature, right? If you increase volume, you're going to increase the temperature. I think I have it backwards, whatever. PV equals nRT, right? Pressure and volume have an inverse relationship versus volume and temperature, right? Volume goes up, temperature will go up if everything else stays the same, etc., etc. These are direct proportionality. Okay, so we have a rate. Our rate is our dy dt, right? Proportional to amount present. So a big useful example right now is there's a direct proportionality to how many people are infected with coronavirus versus how many people are sick. The more people that have it, the more people are going to get sick. It's this exponential growth. There's lots of videos out. You can look at it. Okay, at time equals 0, y naught is the amount we initially have. So guess what? You've probably seen this before, right? We solved this using separation of variables. This is, a part. You've seen this a lot. So I'm going to, I will derive it in example 2. I think we'll be fine. Okay, the constant k is a growth constant. Growth if it's greater than 0, decay if k is less than 0. So right now we have growth of this virus because, it's increasing. We're getting more and more people. And so we have a growth constant. And the scary thing is right now the growth constant's actually increasing. Okay, so if the interest is added continuously, all right, so that's a rate of change. Now, the bankers came in, they're like, we want our own thing. So if interest is added continuously at a rate proportional to the amount in the account, so this is like student loans, right? Your interest, you can get interest on your interest on your interest. We can model it using initial value problem. All right, the differential equation, we have our rate, we have the amount of money, and the initial condition, how much we start with is A naught, the amount after t years, A naught equals e to the RT. Okay, so population y grows according to the equation dy dt equals ky, where k is a constant, t is measured in years. If the population doubles every 10 years, what is the value of k? All right, so we have a direct proportionality. All right, so dy dt is equal to ky. So dy dt is equal to ky. So if I separate the variables, I have 1 over y dy is equal to k dt, right? Take the integral of both sides. I get ln, absolute value of y, is equal to k times t plus a c constant. Raise each side to the power, put each side as e to the power of it, right? E to the ln of absolute value y is equal to e to the kt, e to the kt plus c. Solve for y. Okay, so here, let's see. I am going to ignore the y, the absolute value, because I know it has to be positive, right? Exponential functions can never have a negative y. That's why I can ignore the negative. So normally I write absolute value of y is equal to e to the kt plus c, but you know, I really don't need the absolute value signs because I know y has to be positive. Exponential functions are always greater than 0, right? They're asymptotes at the x-axis, so the y is always positive. Okay, let me break, all right? So if I have e to the kt plus c, that's the same thing as saying e to the kt times e to the c. Because if you would go backwards, right, you would add the exponents. Okay. Well, e to the c is just our constant. So I have y is equal to e to the kt times c. So when our time is equal to 0, y naught is going to be e to the 0 times c. So therefore, our y naught value is our constant, all right? So this is how, because this is, let's see, right here, right? This is at time equals 0, y is equal to y naught. Right, that's our initial amount. So this is how we get y is equal to y naught e to the kt. That's exactly, we just derived it. Woohoo! Okay, we're only going to derive it this one time. Right, the rest of the time we'll go straight here. Oops, not right there. We're going to straight there. But this is, right, it's not willy-nilly, right? This didn't just come out of thin air and drop down in your previous classes. This is how we got it. We literally, people did separation of variables, and that's how they found a part, right? That's true of the majority, actually all the formulas that you're ever going to have. They either are observable, right? So people found it using experimental data, or calculus. This is where calculus comes into play. Okay, so we have our equation we're going to use. So now let's do the problem. All right, it grows according to this equation. Dope. All right, k is a constant, t's in years, population doubles every 10 years. Okay, what this means, so I'm going to use my y is equal to y naught e to the kt. All right, it doubles, so that's 2 times my initial every 10 years. So I'm going to say k times 10. All right, so after 10 years, we have twice the amount of our initial population. So if I divide by y naught on both sides, I get 2 is equal to e to the 10 times k. Okay. Let me take ln of both sides. So if ln is, ln of 2, sorry. ln of 2 is equal to ln of e to the 10k. So this is just going to be ln of 2 is equal to 10k. If I divide by 10 on both sides, ln of 2 over 10 is equal to k. Now this is a perfectly good answer, right? This is a good enough answer for calculus. That's totally fine. If you're not happy with it, I'll show you. Okay, this is equivalent, approximately equivalent 0.0693, but this is fine. This is the value of k. Awesome, awesome, awesome. Okay, let's continue on. I have 2 more problems. All right, so example 3, a puppy weighs 2 pounds at birth, 3.5 pounds 2 months later. If the weight of the puppy during its first 6 months is increasing at a rate proportional to its weight, okay, proportional to its weight, so how much it weighs is gonna influence how much weight it's going to gain. So our rate of change of the weight, dw dt, is going to be proportional to how much it weighs, so k times w. This means we're going to use w is equal to w naught e to the kt. I could go through the whole derivation. I did the second example, but I don't need to. Okay, we want to know what is its weight when it's 3 months old. So w of 3, all right? What is its weight? So first we have to find k. So I have w is equal to, well, let me rewrite it. W is equal to w naught e to the kt. So my initial, let's see, my final weight is 3.5. My initial weight is 2 times k to the, let's see, it was 2 months later. So here it's going to be in terms of months, right? Context of your problem. It could be in years, months, etc. Okay, divide both sides by 2 and then take ln. Well, I'll show you. 3.5 over 2 is equal to e to the 2k. Then take ln of both sides. Right, ln of e to the 2k, ln of e, that part cancels out, I'm left with 2k, divide by 2 on both sides. So if ln of 3.5, let me rewrite it nicer. ln of 3.5 over 2, all over 2, is equal to k. So this is just going to be about 0.2798, right? That's fine. Honestly, you could leave it this way. That's coolio, but then I told you what it's going to be equal to. All right, we found K, but really we want to know how much does it weigh when it's 3 months old. So we got to do that math, right? W is equal to W naught times e to the 0.2798 t. So it weighs 2 pounds at birth, so that's going to be a 2 right here. 2 times e to the blah, blah, blah. All right. Sorry, I should be better about this. Okay, so 2 pounds at birth, e to the 0.2798 times 3 months. Plug this in, you'll see it is 4.630 pounds. And units are very important. You can't leave the units out. All right, pounds, we can have 0.63 pounds, that's fine. But humans, no. All right, and here comes the time when I made this before Corona kept us at home. So example 4, during a certain epidemic, not the coronavirus, we will explore that a little bit in depth later. The number of people that are infected at any time increases at a rate proportional to the number of people that are infected at that time. If 1,000 people are infected when it's first discovered, 1,200 7 days later, how many people are infected 12 days after the epidemic is first discovered? All right, so 1,000 people, that's at time equals 0. 1,200, that's at time equals 7. So if we're at 12 days, okay, later, how many people are infected? Okay, so the rate of change, KP, all right, that's the rate at which they're being infected. Now you could use I, but personally I like using I for current. All right, so doing the derivations I did before, I'm not going to redo them. I get my initial amount times e to the KT. So if I end with 1,200 and I start with 1,000, and this is, let's see, we have to solve for K. And that's 7 days, we can solve for K. So 1,200 divided by 1,000 is 1.2. It's equal to e to the 7K. Take ln of both sides. So ln of 1.2 is going to be equal to 7K, because remember, ln of e, blah, that goes away, of 7K, divide by 7 on both sides. So I have ln of 1.2 all over 7 is equal to K. So that's 0.026. And then I must find how many people 12 days after it's discovered. Okay, so P of t, right, I'm just making a function with respect to t of how many people are infected. P naught e to the KT. So P of 12 is going to be, let's see, it originally had 1,000. E to the, let's see, our 0.026 is our K. Notice it's positive. Times our time of 12 days. This is in terms of days. So P of 12 is going to be 1,366.901. So this is going to be about 1,367 people. Because remember, we can't have like 0.9 people. We got to round. Cool. And then that is it. Let me know if you guys have questions. This is the last portion of chapter 6.